So let's get started talking about how we can prove some things about regular languages. Now, before I do any of this, please, 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 if you haven't watched my lecture on how to write a good proof and how to go about doing a proof, please watch that first. It's so important that you watch that before you watch this. Okay, if you look on page 744 of your textbook, you will see a big chart, which also happens to be right here on the next slide, that has a list of all sorts of properties of regular expressions, things that are true about regular expressions. And here's just a selection of a couple of them that if you look at, hopefully you'll say, oh yeah, that kind of makes sense. So let's suppose that R, S, and T are already regular expressions. Then I'm hoping it should make sense that R plus T equals T plus R, right? Plus, in regular expression land, is essentially union, right? So if you take the union of two sets, it doesn't really matter what order you have in it. If you take a set and union it with the empty set, that's the same as unioning the empty set with the set, which is the same as just the set itself, right? Unioning something with the empty set doesn't add any more information. If you take a set and union it with itself, well, that's just itself. The union operator is associative, right? So if I take the union of R and S first and then union with T, it's the same as taking the union of S and T and then unioning with R. So if you look at the textbook, you will see on page 744 this big long chart with all the different properties of regular expressions that we're going to be using. And these properties really are important for us. So they're going to help us to compare different regular expressions for equality, to simplify regular expressions, basically to do all sorts of things with regular expressions. So we're going to do two different things in today's lecture. The first is we are going to prove some of these, right? We're going to take what we know about the set operations, and we're going to use what we know about set operations and what a regular expression's definition is to prove some of these properties. And we're not going to prove all of them, but we'll prove some of them just to give you the idea that, yeah, you could prove these. And then once we've proved them, we're going to use these as axioms for other proofs that we're going to do. So let's do an example proof. And we're going to prove a few of these properties using both the facts we know about how sets work, combined with the rules that tell us how to convert a regular expression into a language and vice versa. So let's suppose that we want to prove that R plus R equals R, right? That's one of these properties that's on that big sheet that I showed you and that's in the book. Well, if you recall, two regular expressions are equal if the languages that they represent are the same, right? I mean, a regular expression represents a set, and so two regular expressions, let's call them R and S, would be equal if the sets that they represent are actually the same set, right? So if we want to prove this equality for regular expressions, what we need to do is prove that the language of R plus R, right, the set associated with R plus R, is the same as the language of R. So here's a proof that R plus R equals R, right? We're going to start out with the fact that the language of R plus R equals the language of R unioned with the language of R. Now, I just got that out of the definition of what does the language of R plus S really mean, right? What do we mean when we say the language of R plus S, right? And it's on page 471 in the book, right? Here was our definition of what a regular expression was, right? And how we'd convert back and forth between regular expressions and sets, right? So if we have the regular expression A, that turns the language of A is actually just the set of A, and so on. So I'm going to say that language of R plus R equals language of R union language of R. That's right from right here. Okay. And then, of course, as I said before, if I take the union of something with itself, well, I just get the language of R. And I'm going to add my QED like I showed you in that video that you definitely watched, right? Okay, now let's prove this property of regular expressions, right? So what does this property say? It says no matter what regular expression you have, if you concatenate it with the empty set, you end up with the empty set. So in order to prove this, we have to show that their languages are the same, right? So the language of R dot the empty set is the same as the language of the empty set. So this one's a little bit harder. I'm going to do this proof sort of the way I talked about doing the mazes and stuff, right? Here's the two things that I want to prove are equal. Let's see what we can do here. For starters, here's just the rules that are going to help us from the book, right? And if I look at this guy, I can say, all right, well, what is this language of R dotted with the empty set? Well, if we look at just the definition up here of what does it mean for the language of R dot S, that's the language of R times the language of S. So same thing here, right? And then over here, if what is the language of the empty set? Well, if you look, the language of the empty set is just the empty set. Now, it's really important to remember that the empty set right here, that's the regular expression empty set, whereas this empty set is a set, right? It is the empty set. It's also a language, right? But this is the regular expression. This is the set associated with that regular expression. Remember that for the empty set, it's just weird and different from all the other options, right? Okay. So now we need to kind of extend one of these or the other. Well, look, we've got this thing over here, right? The language of the empty set we just said was the empty set, right? We can say it again over here. The language of R times the empty set by the definition of what the language of the empty set is. And again, this one's a set, this one's a regular expression. So now we're concatenating the language of R, well, the language of R, that's a set, with the empty set. So we're still good. Okay, and where next? Well, if we look at this as though we're sort of in set land, right? I have two sets here. I have the language of R as one set. I don't know what's in there. And I have the empty set. And I know that if I concatenate the empty set with anything, I get the empty set. So I can just say this equals the empty set. And so now I've got everything that I need, but I still need to lay it out beautifully. And oh, I forgot to tell you, on my slide, this is just an example, right? So if I have for what it means to concatenate two sets together, right? And it just means you take one thing from here and one thing from here. So if I'm taking AB concatenated with DE, I end up with, well, A plus D and A plus E and B plus D and B plus E, and that's all great. If I concatenate anything with the empty set, right, so this is just an example. This is not proof of this, but it's an example. Well, I take A plus nothing. I don't have anything to put in there. I take B plus nothing. I don't have anything to put in there. So anything concatenated with the empty set actually equals the empty set. All right. And as I was saying, I'm not quite done. I still need to take this proof where I've got some of it going downwards and some of it going upwards, and I actually need to write it up nicely. So here's the first part of it, right? This is what I had with my, on the left side of that piece of scrap paper, right? And I just copied it down here and I gave myself numbers. So step one is what I had on the left side, and then equals, right? And so on with my reasons on the right. And then I do the backwards up. I had only one statement on the right, which was the definition of L of the empty set. And that's how I got from here to here, but now I need to use it to get from there back up, right? And my magic QED. Now, for sure, we could prove all of these things. We could go through and prove every single one of these properties, but let's not. What I'm more interested in doing is using these as axioms to do things like take a regular expression and simplify it, or to prove other things. And what I'm going to say is when we do that, here's what the book looks like. The book just has these properties of regular expressions, and it numbers them. If you go on the class website, you will see that you can actually download my handout, which I encourage you to do right now before you watch any more of this video. Just download this handout, and I give you not only the content from the textbook, but also what, for purposes of our class, we're going to use. What are we going to call each of these rules, just so that we can be a little bit more specific about which rule we're using. So here's the first half of the sheet, just to show you my list of things on it. And here's the second half of the properties and the second half of my list of stuff that you can get on the website. Okay, so here's a problem from the book. It's actually asking us to simplify a regular expression. I'm going to ask you to do a little more. I'm going to ask you to justify how you did so using the properties of regular expressions. And I'm going to ask you to use the names from my handout. So you need to have a printout of this thing now. Print it out, take a look, or have it up in a window next to this video. Okay, so one of the things that we can take advantage of when we're trying to look at regular expressions is, in a lot of ways, our gut intuition about how to simplify them that we have sort of a gut intuition from algebra actually mostly works. So like we can use the distributive rules to multiply stuff out. I'm going to informally say multiply stuff out, but really I mean use the distributed properties of regular expressions, right? So if we look at this first expression here, we can multiply it out, right? And by the way, when I say simplify here, right, multiplying it out doesn't always seem as though it's going to be simplification, but let's just see. Let's multiply it out and then see if we can get rid of some stuff, right? That's usually how these things are going to work. So I'm going to use the distributive 3.1 rule to multiply this first piece. And you can see that I can use this rule if I just sort of set R to be the AA part, S to be the B star part, and T to be the A part. And so I get AAB star plus AAA plus the same thing that I had at the end before, right? Now, the important thing if you're doing this for homework in my class is not only do you have to just write out the simplification, you need to write the reason using my terms, and you need to tell me, what did I use? I used distributive 3.1, which has an R, an S, and a T, and R was AA, S was B star, T was A. So you need to give me all this information. So now if you look at this and you look at your giant handout and you think, what else can I do to simplify my newest result? You'll probably say, oh, look, I could use distributed 3.1 again, right? So let's use distributed 3.1 again, right? And multiply out, I'm going to say colloquially, that second part. So we use distributed 3.1. And this time my R is the letter A, right? R is the thing before the parentheses. My S is going to be the AB star, right? And the T is going to be AA. So when I get to this row, I say I use distributed 3.1 where R was A, S was AB, and T was AA. So now let's take a look at this and see if you can think about what can we do to make this even more simple. And you kind of look at it and you say, oh, look, I see some duplicates. And you need to sort of look over that handout sheet that I've given you to start getting a feel for what's available in there. And you also need to just understand regular expressions. And when you think about regular expressions and you remember that plus is union, you say, oh, look, I'm unioning some duplicates. plus properties in here, right? And one of the things that you might notice is that actually you're adding two of the same things together, right? And if you notice that, then you can see that you could actually just use plus 1.3 here, right? So you could use plus 1.3, and what you can do is you can say, well, if I'm adding two of the same things together, by plus 1.3, I just get that thing once, right? So I have AAB star plus AAA by plus 1.3, where, and this should say R equals, right, AAB star plus AAA. There you go, fixed due to the magic of computers. So R equals AAB star plus AAA, right? And now you look at this and you say, boy, I'm not sure I can simplify this anymore. Maybe I could pull out an AA and use a distributive property again. But this is pretty darn simple. A lot of the time when you're asked to simplify regular expressions, some of it is a sort of, it's a, you know, I think it's simple enough now kind of judgment. So yeah, this is probably simple enough. You could also change it to AA times the quantity of B star plus A if you wanted, using another distributive rule, but I think this is pretty good. I'll show you how to do that in a minute. But let's suppose that you didn't notice plus 1.3, right? So let's forget this step for a minute. And let me just show you a couple of other ways that, or another way that you could have done this. So here we are back again at this step. And another thing you might notice is, look, I can combine, right? Plus means union. So I could combine this AAB star with that AAB star and just make it one of them. And this AAA with this AAA, just make it one of them by the rule plus 1.3 also. But in order to do that, I need to have them next to each other. And I don't yet. So another thing that I could do is I could use plus 1.1 to just swap these first two around, right? So I could say, well, these guys can swap around by plus 1.1, right? Where R is a AAA and T is AAB star, right? And once I've flipped them, then I can use that combine rule to combine the two AAB stars. And so I just say I'm using plus 1.3 and R is AAB star. And then I can do the same thing again on the AAAs. And I can say I did plus 1.3 again on the AAAs. And now, like I said earlier, we have a choice. This is simple enough for me, and if you like it like that, that's fine. Your other option is to say, oh, look, you know what? I could use distributed 3.1 to simplify this even more. I don't know if you considered simplifying it even more or not. Again, this is sort of a matter of taste. So by distributed 3.1, if I let R be these two A's, my S be this B star and my T be kind of the A at the end, right? So R is also these two A's. Then I can get that equal to AA times the quantity of B star plus A. As far as I'm concerned, either of these as your last step is fine by me. Both of these look equally simple to me. I actually think that looks more simplified than that, but some of you may have had some math teachers who will put your gut into doing it this way, and that's fine. Both are fine. So let's try another problem from the book. Here we're asked to prove the following equality of these two regular expressions. So we're going to have to do another proof, and let's set it up the way we always set up our proofs. We're going to put one side of the equality, right, the left side of the equality on the left side of our page, the right side of the equality on the right side of our page. Oops. And because I'm such a fan of the distributive properties rules, I kind of think, oh, well, let's see, can we do anything with distributed? And so, of course, I could use distributive properties on this one. So I'm just going to do that as my first step just to see what happens. So I can use distributive 3.1, and I end up here, right? So This thing, if I multiply in colloquial terms, right, it's a regular expression. I'm not really multiplying, but if I use distributive 3.1 here where I say, okay, well, let my R be A star, let my S be B, and let my T be A B star, then by this rule, distributive 3.1, I end up with this as my result on the right-hand side. I'm such a fan of the whole distributive rules. I'm just kind of looking and I see these AAs here, right? The AA star. Maybe I kind of simplify that or unmultiply that out. So I can do this, right? That's also distributed 3.1. And this time I'm kind of using the rule backwards, right? I'm going from the right side to the left. And now you just kind of have to stare at this and say, wow, what can I do now? Where am I trying to get to? Where am I? And, you know, I was looking at this for a while and I said, ooh, this looks kind of good, right? I got this B plus AB star everywhere, so maybe I can do something with that. Right, it almost feels like I've got 2 here. I should be able to do a distributive rule. But I need the equivalent of a 1 times this in math, right? And what's the equivalent of a 1 times this in math? Well, it's a lambda times this, right? So I can use this dot 2.2 rule where I say let my R be B plus AB star. And I can take this piece here and turn it into this. Because once I've done that, then I could use one of my distributive rules again, right? So now I can look at this and say, oh, look, I have something times B plus AB star and another thing times B plus AB star. So actually it looks like I'm going to use this distributive 3.2 for a change, right? And if you look at this, you know, this S piece, right, is going to be a lambda. Again, we're using the sort of go from right to left of this, right? So I have lambda times B plus AB star. So S is my lambda, and my R is going to be this B plus AB star, right? This piece on the right. And then I also have this AA star times B plus AB star. And so by distributive 3.2, I can get down to this. And now you sort of take a look at this again and you say, what have I got on this side? What have I got on this side? Remember the whole maze analogy, right? And, you know, look, these guys are so close, right? Is there anything that I can do here? And so I look at my magic sheet and I say, wow, look, if I look on the closure properties, and anytime, right, star is closure, right? Anytime you got something with a star that maybe you want to mess with, looking at your closure properties is good. And look, I have R star equals lambda plus RR star, right? So I can use that rule. Fantastic. So by closure 5.2, I can say that this whole thing, these 2 pieces, the lambda plus AA star, that just collapses, right? Lambda plus RR star collapses into R star. So lambda plus AA star collapses into A star as long as I have R equal to A in closure 5.2. So now if you take a look, actually, I didn't need to do that distributed multiplication thing here, right? I got from here, I'm at what I was trying to get to. So I'm at the end of the maze, right? So forget this extra step. And now we can take this scratch work and say, I just need to take this and kind of go down through these steps, and I have my proof. And before I turn it in, I need to write it out beautifully. So here's my writing it out beautiful version. So here's another proof from the book. I want to prove that this is equal to this, right? And so, of course, we start by getting some scrap paper and just doing some scratch work, right? So I put one equation on the left-hand side, one equation on the right-hand side. I have my properties of regular expression sheet near me so that I can do this, right? And of course, as I said before, I like to just distribute stuff out if I can. So I look at this and I say, ooh, look, I can multiply it out, which really means in this case, use distributive 3.1, right? So I multiply it out, and I can see that when I do this with distributive 3.1, here's what my R is, here's what my S is, and here's what my T is. And now you just got to stare at this a little bit and say, ugh, how can I get from here to here? And when I look at this, I notice these guys. And I have A star, A, B star here. And I have A star, B star here. And I remember from my closure rules, or I have my closure rules nearby. And I say, can I turn A star A into A star? I mean, if I think about it from a regular expression point of view, this says 0 or more A's and then at least 1, or start with 1 and then have 0 or more afterwards. And those are obviously, to me, equal. So there must be a rule in here that, that actually says they are, in fact, equal that I could use. And sure enough, I look, and closure 6 lets me do exactly that. So I'm going to do it on the right-hand side. I'm going to say B plus A star B star is the same as B plus A star A B star by closure 6, where R was A. And now, you know, I'm looking at this, and I have my A star A B star here on the right, and on the left, I guess that circle really should be down a little bit. There you go. So I mean, I'm looking, I have something plus A star A B star here, something plus A star A B star here. On the left, I have A star B. On the right, I have B. Well, I mean, for sure, 0 or more A's followed by a B isn't equal to just a B. But I'm thinking maybe I can get at least the B alone, and that might help me here. By this rule, right? R star equals lambda plus R star. So I could turn this A star into a lambda plus R star. And when I multiply it out, I'll have a B, right? So I can say by closure 5.2, this expression equals lambda plus A star times B. Because if I just make R the single symbol A, then A star becomes lambda plus A star. So I get here, and, you know, it's not easy. This kind of stuff is not easy. You just have to do a lot of mulling. But look, over here, it looks like I can use distributive again, right? That was my whole point when I did this in the first place, right? So let's look at this. I have something times B, so I guess it's going to be distributed 3.2 in this case, right? And so now I've got B plus A star B plus A star A B, and yeah, I'm kind of hoping maybe I could do something with this. I don't know. I mean, for sure, this expression on the left is not equal to B. You know, I'm kind of thinking maybe I can do something with this. You know, I've got A star B and A star A B star. You know, maybe I can use you know, distributive property. Oops, sorry. You know, I can turn this into A star B plus A B star by distributive 3.1, right? You're kind of used to this. I get my reasons. But now I'm wondering whether really I'm getting anywhere, because this sure doesn't look like I can turn it into that. You know, I'm looking at this, I'm not feeling so good, especially because, yeah, look, this is kind of, I sort of multiplied it, you know, I took it up, I used the distributive before to pop it out, and now I'm using the distributed part to put it back together. This just isn't feeling great. I hate to say it, but it is possible that that maybe we need another approach. Oh my gosh. I'm kind of going to backtrack in my maze a little bit, right? You know that you know, sometimes you try something and it doesn't work, and you kind of need to try something else. So maybe we'll just cross this stuff out and let's try something different. Let's think what else we could possibly do. So I'm going to I shrunk this down and put a little X on it so, you know, I won't lose it. If you were doing this on paper, I just, you know, start another piece of paper or something. I want to show you, here's the work I did. I'm not going to totally erase it because it might prove useful. But I'm just looking at this piece again, and I really feel like, you know, oh, it would be really helpful if I could just sort of get a B out of here somehow. Maybe I can do something a little bit different. And, you know, of course, I want to do some sort of a... probably something with closure, right? A rule, one of the closure rules, because I've got that star in there. And I'm thinking maybe this would be helpful, right? Maybe I can use this r star equals lambda plus r star. Closure 5.2, piece of closure 5.2, right? Because closure 5.2 is a bunch of things, but this piece, maybe that'll help me. So I'm going to turn a star b into lambda plus AA star B, right, by closure 5.2, where R equals A. And now, of course, I have something I can distribute out. So let's use distributive 3.2, right, because the B is actually after the parentheses here to multiply it out. So now I've got B plus AA star B plus A star AB star. Okay. And you know, there I've got my A star AB star. And yeah, this looks interesting to me, right? I have B plus some stuff, B plus some stuff. I mean, over here I've got AA star, and here I have A star A, and I know there's a closure that lets me mess with that. So, here we go, closure 6 over here, right? R star R equals R star. So we could try that. So now I have A star AB plus A star AB star. Well, you know what? I really like using distributed properties whenever I can. Clearly, I can at least pull out the A star A out of these and see where I get. So I can have A star A times B plus B star. This is looking good. This is looking promising to me. Because B star means 0 or 1 B's, right? All in a row. And there's just 1 B all in a row. So I should be able to find something that lets me say, oh, well, this plain old B is a part of B star already, right? So let's look at this and let's take a look at our closure options again. And look at that. There we go. Closure 5.1 lets us say that R star equals R plus R star. So, my circle got moved over here, but, or moved down a little bit. There we go. That's a lot better. So I turned my B plus B star into just a plain old B star by closure 5.1, right, where R is B, using this rule up here. And I think maybe we did it, right? Because now I have B plus A star AB over here. Sorry, B star plus A star AB star here. I got B star plus A star AB here. We just need to write it up neatly. Again, I need to write these ones in the forward direction and then continue and go on with this, with the rest of it, so that what I'm doing, because remember, I want to prove that this equals this, I need to do it in one direction with all my reasons. So here you go. Beautiful. Here's a proof that A star B plus AB star equals B plus AA star B star. Notice that on my first step, I have the thing on the left here, A star B plus AB star equals, and then I go through all my steps, right? So this is just my first step here, right? And then at the very bottom, the final thing I have is B star plus AA star B star. And let's never forget this QED. So I'm going to give you one more example of a proof, another one from the book. And I'm not going to go into quite the same level of detail that I did before. You're going to need your sheets with my names on them nearby just so you can see what's going on. But hopefully this will be useful to you. Let's prove that this is the same as that, right? That these two regular expressions are equivalent. So what I'm going to do is I actually kind of pre-circled some of these pieces so that you can see what I'm doing with my proof. So I'm starting with this expression up here on the left, and I'm working towards the expression on the right. Right? And so, of course, the first line that I put in here was the same as the expression on the left. Here's my next step. And what I've done is to try and show you which piece is R, which piece is S, and so on. I've just circled them. So what I've got here is up at the top I have R plus S star, right? So that really tells us that this A is R and that's S. And we can see that that is in fact equivalent to, you know, by the closure 7 rule, that's equivalent to R star S, quantity starred, R star whatever, but you can see that there's our R star S, and we star the whole thing, and then we have R star, right? So we left the stuff outside the parentheses the same, and we used closure 7 rule to do that first step. Now what I've done here is I've just erased the circles. So that's what it looks like if you don't have circles, because of course in a real proof you don't circle things in fancy colors. So here's my next step with circles. So I'm showing you how did you make that leap, and the reason is closure 8. And in this particular proof, you don't have to do this in your proofs, though it may help you. I've said, what is closure 8, right? What is the piece that I'm using here that tells me what's going on, right? And again, you can see that the expression R is just the single symbol A, and A star BB star is my S, so that gives me that RSR star is the same as RS star R. So by closure 8 we can make that step. Again, same thing we had before, I just got rid of the circles. Now I'm showing you how I did this step. I say that I did this step between these two by using this rule, and I've just stuck the circles in here again so you can see what's going on. So we've got our B is now our R, and this whole green stuff is our S. And there's our R again, so you can see we have something of the form R star, and then the parentheses, and we have S R star star, and we just change that to R plus S, quantity starred, just like the closure 7 rule says we can do. And whoa, look, did you notice? We actually got what we were looking for. So we get to write QED. I am done my proof. I have proven what I intended to prove. Yay.